Hello, this is the third question in the January 2011 Unit 2 past paper. Now, this sort of looks a bit confusing, really. Probably my drawing, to be honest. But what it's showing is the maximum of a single slit? Yeah. Diffraction pattern produced on the screen using a laser. Now, we don't need to worry so much about the laser bit at the first question, but all the first question is asking us to do, now if you know your physics, it's quite simple. If you don't, you're sort of stuffed. Basically, the distance increases from the screen, and you may see these like individual sort of lines, vertical lines along the horizontal axis. Now what this basically means is there are fringes that occur at the, well, not fringes, maximums is what they're called. So there's single points of highly concentrated light. Basically it's just the diffraction where all the light's concentrated, where it superimposes, but we'll go into more of that in a minute. It's just asking us to finish drawing this. Sorry, that's actually not correct, really. Should I'll stay in the first bit. I'm going to draw the first bit in red, which is what it gives you. So that's the first. These are maximums. That's the first maximum, second maximum, third maximum. What you normally get is a maximum of about three maximums, really. You can see more there, but the more you go down past three, the harder it is to spot them because they sort of intertwine into others because they become so fuzzy that you can't tell when one ends and one starts, and that sort of distort it. So basically that's why there's only three there. So at the maximum it goes up to sort of, it's straight like that. So is that sort of right? Just need to make sure I'm doing it right here. Yeah. So it's not straight up, sorry. So it sort of curves and it sort of goes up, and it goes up again, goes up. Now we could keep doing this. As you can see, basically the main thing you need to know is that the maximums, the intensity, notice the intensity up here, it gets less every time because the superimpose is less, as the angle of diffraction means that the imposing light waves, the transverse waves, create a, transverse waves. You say light acts as a wave, which is, or like as a particle, which is per photoelectric effect, which is unit 1. So basically, all you need to know is the intensity reduces because the accuracy decreases. So that's, I mean, there is a proper scientific explanation for that, but basically the intensity decreases. So the next question, we sort of talked about this before, so that's part A. The part B. Now we sort of mentioned it before, but I didn't go into too much detail because this is what this question is asking. Now it says laser is a source of monochromatic coherent light. State what is meant by monochromatic light and coherent. Now monochromatic light is light of a single wavelength. I can't really explain a bit more than that. So monochromatic is a single wavelength. So you can't put anything else. A single wavelength or single lambda, whichever you want to imply. So single wavelength. So if it's a single wavelength and then coherent, basically for coherent, understand what it means. We need to sort of go back to our understanding of diffraction and why we do it. Now we use a single slit diffraction to split it up into two sources of coherent waves. But is a single slit? That's why they can say laser is a coherent light, because they only need one slit. It's already coherent, which we'll explain that in a minute. So you don't need to split it into two. That's why it's only one. But the coherent basically means it's the same phase difference and the same amplitude. So it's same phase difference or same PD. I know that means potential difference, but it's phase difference in this context. Phase difference, same phase difference, and same amplitude. And that's pretty much it for the part B. Only 2 marks there, quite easy. Now it says for this 3C, explain how the pattern would change if a longer wavelength of light was used. Well, basically, if a longer wavelength of light was used, what we'd expect to see is that the maximum is further apart and the central maximum is wider. That's your mark, basically. That's because the wider the wavelength, the more these maximums increase, because they are sort of imposed for a longer amount of time, if you can imagine it like that. So basically the maximums, width of maximums increase. And if you don't believe me on that maximum, these are essentially fringes, which is, we talked about Young's fringes. I know this is single slit diffraction, so the wavelength, the fringe spacing is W equals 2 lambda D over S. That's the equation for fringe spacing. Now I did just remember that off the top of my head actually. So if we increase the wavelength and we don't do anything to anything else, we increase the fringe spacing. So the fringe spacing is the same as a maximum spacing in the case of single slit. So what we're doing is we're increasing the fringe spacing or single slit maximums. So that's what we're talking about there. So that's why we can say the width of the maximum is increasing. Hopefully that's proved it to you, how the wavelength increases. I've not just pulled it out the mark scheme, or technically I have, but I haven't pulled the equation out, and I've tried to explain it in a bit better way than it does in the mark scheme. I don't think it's it's convenient for you. Not convenient, sorry, if that sort of works for you. So it says, describe, 3D, it says, say 2 ways in which the appearance of the fringes would change if the single slit was made narrower. Now the slit spacing is S, so if the S is made narrower or smaller, given a smaller value, then the fringe spacing increases, so the width of the maximums would also increase. So yeah, so the width, the maximums, they've worded it in the mark scheme, as you get used to doing it that way, is wider separation. The maximums or just wider separation, really. That's all you need to put. So 3D is wider separation. Oh, it says state 2 ways in which the fringes. So you need to state another way, and another would be if the wider separation is less concentrated at one point, just as it's spread out as the spacing is smaller. Sorry. So wider separation, and if it's less focused on one point, it's less intense. So the intensity is reduced. As you put inside reduced intensity. 3E, it says the laser is replaced with a lamp that produces a narrow beam of white light. Sketch and label the appearance of the fringes you would expect to see on a screen. Sorry, just see if they draw a diagram or anything. Distinct fringes. Sorry, I'm just going over the marks and making sure I understand it before I explain it to you. I mean, obviously I do, but just make sure I don't miss anything out in my explanation. So, distinct fringes. Sorry. So this is for 3 marks. So you need to state. I was going to draw anything. It says sketch and label the appearance of the fringes you would expect to see. If the narrow beam of white light. Now, if you remember your spectrum, white light is it contains many wavelengths, so many colours of light. So we'll sort of sketch the same sort of thing, I think. Oh, so yeah, sketch the same sort of thing as that up there, part A. So it'll look something like this, and it should be symmetrical on either side. Mine isn't perfect. No, it's not. But basically, all you need to state is that at the centre of this, you have a strong white light, but then you've sort of red and violet on each side as you go out, and it sort of goes to blue. and a couple of maximums. But you need to state, one of the main things you need to state is the central maximum is white. But obviously, with a wide range of wavelengths, it changes colour as it goes further distance away, and more maximums. Obviously, these are all maximums that you've got there, same two maximums. You need at least one maximum on each side, is what it states. So that's pretty much what you state. That's the end of question 3, actually. It's quite a quick question, really. There's not that much to it. Hopefully that's given you a bit of a guide to what the question's asking you. So all you need to remember as an overview from question 3 is that the intensity reduces as you get further away from the maximum. You get more, a central maximum even. And for the monochromatic light, it's a single wavelength. Coherent is the same phase difference and amplitude. 3D, which is, it says, you just need to remember this equation, W equals 2YD over S for the single slit diffraction, and obviously for Young's modulus, Young's diffraction of light, so double slit diffraction, you've got W equals YD over S, or you can rearrange that to get Y, but I just leave it as that, so you could use that to explain changing the wavelength and slit difference, which it gives you that in the equation in your formula page even, but it doesn't give you the 2 lambda d over s, but you just need to remember that. And the white light, if you put a white light there, it's many wavelengths, so it splits up as a white in the centre, and sort of you've got the sort of red and violet fringes on the outside as you go towards the end of each sort of fringe. That's the end of question 3. Hopefully that's sort of enlightened your brain into physics. We'll see you in the next video.